So EOmaps, the package that I'm going to show today, it provides also a more fine-grained way of managing dependencies nowadays with pip. But for the workshop and for the context of simplicity, we'll try to, we just use all in here to install both the visualization packages and all the others that you need for data access, like pandas, X-array, and others. Anyone already managed to install the thing? Yes? Ah, sorry. Yeah. So be patient, it might take a few minutes because it installs a lot of packages, including PyQt as a visualization package and others that are a bit larger. It's not necessary, it's an optional dependency, but it helps a lot in working with interactive visualizations. Okay, are we good with the link? Anyone still needs to read it? So otherwise, let's just dive into this. So what's this workshop going to be about? So it's going to be about EOmaps. EOmaps is a package I've been developing in the last, well, several years now, and it somewhat contains all the things I always wanted to have in terms of geographic data visualization. So me, myself, I'm Raphael Quast. I work currently at the Technical University of Vienna, and I've worked for several years with geographic data analysis, mainly in Python. And I used extensively Matplotlib and Car2Py and others to analyze my datasets, but well, they are extremely powerful, but to some extent a little tough to use sometimes, especially when it comes to interactive use cases. And this made me start to develop EOmaps, which is basically an interactive layer on top of Matplotlib and Car2Py to deal with interactive geographic data analysis. So the idea is to make the visualization process simpler, to have a dedicated package for geographic data analysis, and to allow you to directly use the maps for interactive data analysis. Yeah, so before we start, as we said, EOmaps is built on Matplotlib, and Matplotlib is not just providing a single backend that allows you to create static images, but it actually provides you a multitude of different backends that you can just switch to create different kinds of visualizations. So in this case, it provides you PyQt to create interactive pop-up widgets made with PyQt graphical framework. You can use the Python native Tkinter framework to create your interactive visualizations. You can embed your images directly in your Jupyter notebook using the Matplotlib widget backend. You can create your static images. That's actually the 99% of the times you actually see this one used, because this is the default. It just puts you a static image in the Jupyter notebook, which is nice, but it actually takes away a lot of the possibilities that you have with Matplotlib. Yeah, and then there's also the possibility to go completely without any graphical user interface, which is going to speed up image export a lot. And it saves you a lot of RAM and CPUs. And finally, you could even embed it in other, so there's the web backends that allow you to embed your images via Tornado web servers into HTML pages. So in our case, we're not going to spend too much time on this. So for EOmaps, the package that it is mostly developed in is PyQt. And for this also, there's a little graphical user interface nowadays that accompanies the library. So we are mostly going to use PyQt in that sense to visualize our datasets. Yeah, so just before we dive in, if there are any questions, please just pop them out. the idea is to make this interactive and to show you how easy it is to actually visualize geographical data sets with this package and how quickly you can use it to analyze your data. So the workshop will be structured into several different chapters, so let's see how far we come with that. Sorry, this thing is... so we start off with a little bit of basics, because I don't know, any of you ever used the package? Very good, I understand that. I'm going to show you the basics on how you can use it and what it can do for you. And after that, after you learned how you can use the basic principles, we dive into data visualizations. We have a look at a few raster data sets, see how we can visualize that. And then we go one step further. We have a look at a whole stack of raster images. We see how we can actually analyze multiple images in one go, how we can use lazy plots so that we have the data ready just when we need them without directly using all the memory and CPU power to create the plots. So these will be happening in raster images. And then the last chapter, I thought I'd show you that you actually not always need two-dimensional data structures for your data sets. So sometimes your data sets don't come in images. Sometimes they actually come in more complex structures. So I've picked out some data sets that are provided in a Fibonacci grid, so in a grid system defined on the sphere. And we're going to have a look at how we can actually visualize this data set without rasterizing it first, or by rasterizing it on the fly. Okay, so this is the overview. So if you click here, you're going to open up the first notebook, which is, I've downloaded the GitHub repository. We start off with the introduction here, and then we dive into the first notebook, which is showing you how the basics of EOmaps works. So in general, I already said EOmaps, it's packaged, it's built on top of Matplotlib and Car2Py, so many of the functionalities come from these two libraries. So Car2Py provides all the general object-oriented access to different geographical projections, and Matplotlib provides the general plotting framework. And so what you do with EOmaps when you want to create a new map is you initialize a new maps object. So this maps object is going to be the general thing that you use all the time. And once you create a new maps object, what it does is it initializes a new Matplotlib figure, and it puts a new Car2Py geo-axis in there. So how can we do that? So let's see how we can create a new map. So first we set the backend. In this case, we switch from the default inline to the Matplotlib Qt backend. So from now on, all the figures are not going to appear inside the Jupyter Notebook, but they appear as interactive pop-up plots that we can use to analyze our data interactively. And then we go on and just import the maps object that will serve as our main access point to creating our maps. And before we create our maps, we directly config some global parameters. So in this case, we want the maps to remain always on top, because that's a nice feature if you want to code and have your pop-up just next by. And we set the logging level so we get a bit more information as we do. And now if we initialize our new maps object, so looking at this, here we have our maps object, the maps object. If we look at the docstring, we see it accepts several parameters. So the first one is a coordinate reference system, which will set the projection of the map that we create. And then everything else is basically forwarded to the Matplotlib figure. So in this case, we directly set the figure size, and we say that we don't want any background color on our map. And if we run this, we get a nice pop-up plot here, and this plot already has a map in it. It starts empty. So this map starts empty, so this means if we want to add something to this map, we get here our maps object back, so our instance, and this instance is what we're going to use to interact with this map. So if we look at what this offers, so the maps object offers you a lot of different methods, but the thing is, I tried to keep the syntax as accessible as possible, so anything you want to add to a map starts with add. which makes it super nice and accessible to find things you want to add to your map. So we can't go through all this because the idea of this workshop was to mainly go into data visualization, but we can have a quick look at some basic features because any data visualization needs a background map. So we can start by adding some features. So the add feature directive here, it just allows you to go to access natural earth data. So natural earth being an open access vector data format. And now we can just browse their vector data directory and see what's there. So we have a few presets, which are just color presets. So we can look what presets are available. We can add coastlines, country borders, lake colors. So if we want to add coastlines to the map, we just execute this, and we have put some coastlines on our map here. We can continue here. So for me, for now, let's just put this away. We can continue here, add some other features to the map, like, for example, we can browse what's available on the physical category. So you see there's loads of different features available. So we can put some ocean coloring on this map, and we can define a custom face color. We make it red, for example, and then if we run this, we get a red ocean coloring. So it allows us, so this is nothing special. Car2Py can do the same thing for you. EOmaps, in this case, just provides you a nice generalized access to the whole database of natural earth. And of course, here you have your map, and your map is not static, your map is interactive, and you can just zoom in and do whatever you want with it. So let's get back, delete these ones, create our initial map, so we can create a lot of them. They stay on top because we set always on top here. So in this case, we just use, so Natural Earth provides the vector data in 3 different scale ranges, so 1 to 10, 1 to 50, 1 to 110. So we can fix this here. The more fine-grained we go, the longer it takes to plot them. The first time you add some feature to the map, it's going to be downloaded. After that, it's caged, so you can reuse it all the time. The same is true for reprojections. So the first time the thing is reprojected into a different coordinate system, it needs to do that, but as long as the kernel stays alive, also the reprojected feature stays alive. So you can, after the first time you create it, so for example, if we go here and say that we want to create this map in Web Mercator projection, now we use the different projection. If I add the coastlines to this map, it takes a while because it first needs to reproject all the features into this projection. So this is taking a while until it's done, but the next time we create this, as long as the kernel remains alive, it's immediate. So it allows you to really quickly recreate the features or the maps that you want. So so let's add some features. This one we don't need. So this is just the add feature directive, allowing you to put whatever Natural Earth provides on the map. So aside of that, of course, there's you need to set some things. So you can set the extent, or you can do some fancy things, like you can make rounded borders, make your map look a little bit more beautiful. So just general functionalities in here. And then in addition, what I've also tried to provide with these packages are some things that are still missing in Car2Py. So some of them I tried to port to Car2Py because this is not a competitor to Car2Py, but it aims to become like just an interactive thing on top of it. So I try to backport whatever's possible. But so here, just to show you a few of the other features, so we can add little north arrows wherever we want to. We can add a scale bar in here. We can put logos on the map. So the idea is I've created millions of these maps, so I want some things to be fast, and I want them to remain interactive. So this credo I tried to do with all the features. So these things that you put on the map, they're not static. You can actually put them somewhere else if you want to. The same is true for this scale bar here. And actually, by default, you can fix this scale bar somewhere on the map, but you can also just zoom in and it's gonna follow you. So it's just a nice little tool that allows you to identify where you are, how big the things are. So you can click on it. If you press plus and minus, you can rotate it. So you actually see that on this projection, the width is not uniform, but actually depending on which direction I look, I have a different measure. So it's a nice educational tool as well, showing you that you should not put a scale bar on a global plate carrier projection, because it's not a good thing to do. It's very much not uniform. So it can also be used as an educational tool in that regard. Yeah, and then last but not least, here now we have our interactive figure that we use to interact with the data, but sometimes you still want to get them static, so there's the snapshot directive that always allows you to just put a static snapshot of wherever you are into the map. So you can zoom out here to whatever you want to, and then just put your static snapshot into the Jupyter notebook whenever you need it. So these are the basics. Of course, there's a lot more on what you can do to create base maps. We're going to see some of the features later, but I'm not going to go into too much details. The idea is to have a really intuitive interface that allows you to quickly create the map that you need and then go from there. So the documentation in that regard, so I just want to pinpoint you to this. So the documentation in this case is really extensive and provides you with explicit pages on all the features and what you can do with them. So really including all the time full code examples on how you can actually recreate those things. So for now, this just showed us, well, how you can create a single map with EOmaps, which is nice, but that was not the main purpose of the package. The main purpose of the package was actually that I got a bit sick of comparing static images with each other, and what I wanted is a multi-layer capability of Cartopy. So what I wanted is to have something like this, so that I can create myself a map containing one map or multiple maps and multiple matplotlib plots, and then I just want to get an additional layer on top of this map and do something else there, and then interactively compare them. So EOmaps provides you with a multi-layer capability, so you can always, once you've created yourself a map, you can create as many layers as you want to, and you can afterwards interactively compare and combine those layers. So I will not let you read this for now, but I will just show you how it works. So let's do the same thing again. When we create ourselves a new map, like this one, this map already has a layer assigned to it. So actually before, I didn't show you, but there is an argument in here telling you the name of the layer that you want to assign your maps object to. So now this maps object, if we check m.layer, it's actually on the default base layer. And now we can create ourselves just new layers. So in this case, the new layer, we just say m.new layer, give it a new name, and what we get back is another maps object. So this mocean here, so if we create these layers, they're immediately created, nothing happens because they're not visible. So any figure that you see in here always shows one layer. But a layer in EOmaps is just represented by another maps object. So anything we've already learned in the first section, we can now do with all those layers. So we can just populate them with features. So let's populate this ocean layer with the feature. So again, nothing happens. Actually, it runs immediately because all the features are lazy. They're only plotted if you show the layer. So you can just populate it with whatever you want to, and if you don't show it, it's not going to be done. So they're populated the time we show it. So let's populate the others as well. So here we put some markers. So another directive we haven't learned yet. So add marker just allows you to put a lot of markers to some coordinates. You give it the coordinates, you give it the coordinate reference system. You tell it the shape of the markers that you want. Then you can just run it again. We don't see it because the layer is not visible. So we can, in order to show one of those layers, what we can do is say m.showLayer. And now we can just tell it the layer that we want to see. So if we want to show the ocean layer, now we see the ocean layer. We've created the markers layer. So if we want to see the markers layer, we could also just use the maps object and say, show me this layer. So apparently we put some markers somewhere on this map. And yeah, so we can continue. We can add finally a few more features. So in this case, we just use our overlay layer that we've created in here, populated with some coastlines, and then we put an annotation somewhere. So if we want to see this overlay layer, let's have a look at it. It looks like this. So it has now some coastlines on it. And again, we can zoom in here and interactively just switch the layer to whatever other layer we have. So it already is quite nice. It allows us to create a lot of layers. Many of the functions in the package already allow you to directly specify here a layer argument. So in this case, it just omits us to explicitly creating a new maps object and then putting the stuff on there, but this is just being done internally. So if I say layer equals grid, then internally it will create a new maps object on the grid layer and put this thing on there. So in this case, what we do is we put some grid lines on this grid layer, and yeah, we just run it. So again, we can show the layers, we can make snapshots, we can show them, but the nice thing is these layers don't need to stay on their own, but you can actually stack them as you want to. So let's just try this in here. So we can start off with the ocean, and then we can put the overlay layer on top. So now we have the ocean layer, and we put the overlay layer on top. So we also created the markers layer. So we can put our markers there. So they are somewhere here now. And these layers, so basically a new layer just represents our matplotlib axis or our cartopy axis, and they all share the same axis. So that's why they all interact nicely and they're not misaligned in any ways. And so you can just stack them statically, but you can also add a little bit of transparency. So show layer allows you to provide tuples. So I can say, please put the markers layer with 50% transparency on the layer below. So it really allows you to nicely keep your features of your maps organized and to quickly compare them with each other. So in this case, we also created a grid layer. So here, in this case, we added some grid lines with a grid spacing of 25 degrees. We added another piece of grid lines. So here we added the grid lines, the light lines that you see in here, and then we put another grid lines here, and we added some labels on the right. So again, EOmaps tries to be interactive, so all these features are as well. Yeah, and all of these things are on individual layers, so you can create them however you want to. So this, for now, it doesn't seem very powerful, but later we're going to see how this can really help you to analyze your datasets, because suddenly you don't need to create a lot of static images, put them in a folder, and then start comparing them with each other, but you actually already have all of them in the map and ready to be plotted whenever you want to show the layer. Yeah. So again, there's much to learn about layer management. And we're not going to go into details into that, but the basics are simple. The basics is you create a new layer, and this new layer is just a maps object. It's just the same thing that we use over here. So anything we can do with the basic, the first one we can do with any of the layers. The only difference is whatever we add to the layer, it only appears on the layer. Okay, so this is all nice, but usually this is the point where interactive data analysis in Python is, well, becoming bulky because actually I don't want to code switching a layer. That's usually the problem. And that's why I created the companion widget over time, which is a PyQt widget. So if you click on your map and press W, you're gonna, press W, you get yourself a nice little graphical user interface in here that allows you to do all these things interactively. So you see this user interface, it always connects itself to the map that you've clicked on. So you can show hide it by pressing W, and it already knows that we've created a lot of layers and they have been interactively stacked on top of each other. So you can pick them and rearrange the order of the map. So we need to go somewhere where we can actually see this. So we can put the base layer on top, or we can show just the grid layers, the ocean layer. So holding Control while clicking on these things here allows me to switch through the layers. Holding Shift while clicking on these layers allows me to stack them. And then changing the order allows me to interchange just the order of these maps. So we can put the grid line here on top of the ocean, or we can put the ocean on top of the grid line. Same is true for the markers. Now the markers layer is all the way to the bottom. We can put it all the way to the top. So now we have the marker on top of this layer. So, and this is where, in my opinion, the package is really starting to get very useful for data analysis, because you can do these things interactively. And it's, you have your map, you create your features, you create a lot of different layers, you just interactively compare them with each other. And the big bonus is you're still in Python. You can still continue coding over here. The map is just waiting for you here. So it provides you with, like this little widget here, provides you with a lot of functionalities. The most important one for starting maybe is the question mark button, which gives you information of all the buttons you can click and what they're gonna do. For example, here we have a little annotation. So if I click now on the map, I get a little annotation telling me where we are. Or here we have a list of the individual layers, so we can also stack them like this using Shift. We have down here a little export section. So this export section serves two purposes. The one is that it's a little bit more extensive way of exporting the images than the save button over here, because it allows you to set what kind of file you want to export, what's the DPI you want to export, how to handle vector datasets, should they be rasterized or not. You want the transparent background or not. If you put web maps on your map, if you want to refetch them according to the export dots per inch, and then a tight bounding box. So you can just put save here and then save the image somewhere. But what EOmaps also does is, in the spirit of interactivity, when you click on your map and press Ctrl+C, it exports the figure to the clipboard. So now I can just open Paint or whatever and import my figure here. So it really allows you to quickly work with your figures, search for whatever you need, press Ctrl+C, Ctrl+V, and you have the new one here. The thing is, this Ctrl+C, Ctrl+V also interacts with this export thing here. So actually I can export my figure as a 300 dpi figure with Ctrl+C. Now pressing Ctrl+V, we have created the same thing in 300 dots per inch. So it allows you to save a bit of time when you have to create a lot of figures, and especially when it comes to research, when all your figures are prototypes. So you really don't need them sometimes to stay for long. You need them to show what you want to show, put it in a report, and then go on from there. So much to the widget. We're gonna get back to that. So that's all for now that I wanted to show you about the basics of EOmaps, because the main topic of today should be data visualization. So let's close this. Any questions regarding this so far? If not, then let's just dive into data visualization. So the repository, if you cloned it, it contains here two folders that contain a few dummy datasets. Both of them are netCDFs. One is a gridded dataset, the other one is a non-gridded one. So, but the general concept of EOmaps was also, when it comes to data visualization, that I wanted to be able to quickly switch the way how datasets are plotted, and that I just want to assign the data and then plot it, and not having to look all the time about the input format of my plot function. So whether the contour plot requires the two-dimensional structure and the scatter plot a one-dimensional structure. So therefore, the way how it's done in EOmaps is actually you create yourself a layer for the data, so a new maps object. Doesn't matter if it's the base one or if it's anyone, so every data set needs its own maps object. And then you just assign the data to it using m.set data. So if we look at the documentation, so this set data function, it accepts several different arguments. So we have the data. So the data in this case can be a NumPy array, it can be a pandas data frame, it can be an X-array data set. And then you have X and Y, which tell you what you want to use as coordinates. So it can be either NumPy arrays again, pandas data frames again, or it can just be strings that identify to the columns that you want to use as coordinates. You have a coordinate reference system argument, which tells you in which coordinate system your data is provided in. So this helps a lot if your data is just a free floating list of coordinates and values, and it's not already a nicely formatted GeoTIFF or netCDF that knows the projection, so you can just plug it in here. It accepts whatever PyProsh accepts. And then there's the parameter argument, which is again a string just telling you which column you want to actually use for plotting. And last but not least, we're going to go to that a bit later. It also allows you to tell if in case your data is encoded. So if you have really large data sets, they usually come as integer encoded data sets to save a lot of space. So there's no need to convert them to floating point numbers before you plot them. You can just tell the library how the data was encoded, and it's gonna handle it internally without converting everything to float. So this is the first step. So we assign the data to a maps object. Then there are two optional steps. So the first is we can tell it how we want to visualize the data. The second is whether or not we want to classify the data. And then the third is we just trigger the plot. So coming to the second step, this is actually, so EOmaps provides you with a lot of different ways how you can visualize your data sets. And the basic idea here was that I want to have at least a few projection-aware plotting shapes. So if I have a random collection of data points, I want to tell the package, please draw circles with a radius of 5 kilometers around each data point. Or please draw circles with a radius of 0.1 degree, or a radius of 1,000 meters in whatever projection you have. So a lot of time I encountered these problems that I want to do that, and it's actually always a lot of work. So EOmaps provides you with these three shapes here to draw rectangles, ellipses, or geodesic circles, where the radius is either defined in a given projection or the radius is defined in meters on the geoid of the projection you're using. Then you have scatter points, which is just non-projection aware size of our points. We can create contour plots, we can aggregate the data as hexagonal bins, we can create Voronoi or Delaunay triangulations, and then we have two-dimensional data structure support. So there's a raster shape using just the native raster visualization, and then we have actually access to data shader. So data shader is a package that is used for extremely large data sets. So if you run into the millions and millions of data points, there's actually no need to visualize each individual data point, but you need to pre-aggregate before you create the plots. So data shader provides an extremely fast way to pre-aggregate the data so that 10 million, 100 million of data points can actually be visualized on a plot in reasonable amount of time. So you can choose between all those shapes, and then you can just trigger the plot. So let's see how this works in practice. So for this, I put, again, I used Copernicus. So what we have in this gridded data format folder here is a few example data sets of the Copernicus soil water index data set. So this soil water index just tells you the wetness of the soil in percentage from 0 to 100 measured by a C-band radar instrument. So not going to go into details into that because we just want to visualize it. So how can we do that? So again, we start off setting the backend we want to use. In this case, we need pathlib to identify our paths in the folder. We import Xarray as the backend that we're going to use to open our files, because if we look at the gridded data folder, all of these files are netcdfs, and Xarray in this case really is the nicest way, in my opinion, to interact with netcdfs right now. And then we just import EOmaps in here. So in order to have a look at the first image, so we just say Xarray open dataset and give it the path to the first image in this folder. And then we can just look at this image, or Xarray just gives us a nice interface to the data that we're looking at. So we see we actually have a dataset containing 3 dimensions, latitude, longitude, and time. It's a 2-dimensional data structure. Obviously, it contains a lot of different variables. So these are soil water index levels at different depths in the ground. Then there are some quality flags for this data set, and then there's a so-called surface state flag that telling us the state, whether the particular pixel was frozen or not, or if it's a water pixel or not. So the data contains a lot of information, and what we want to do now is we want to visualize this with EOmaps. So how do we do that? So first, to start off, we get rid of the 3rd dimension because we want to visualize a data set, so we want to have latitude and longitude in there. So we just select the first time index, and then we create a new map. So we create ourselves a new map. We put some features on there that we have a nice background map, and now what we do is we want to visualize the soil water index 40 layer. So what we do is we create ourselves a new layer, and then we just, we can show this layer. It looks the same as before. The reason for that I didn't say before is there's one special layer. It's called all. So whatever you add to the all layer appears on all other layers as well. Which is the reason that if we look at the widget, now we are at the SWI 40 layer, but it looks the same as the all layer, because the all layer, everything you add to this all layer appears on all layers. Now that we have created ourselves this new layer, we can assign the dataset to it. So we use set data. So we assign the dataset to this layer. We give it the Xarray dataset that we have over here. We tell it that the x coordinate should be longitude, the y coordinate should be latitude. The parameter we want to visualize from this multitude of variables that we have in here is the SWI 40, this one. And the coordinate system of this latitude longitude is actually provided in this variable here. It's 4326, but let's do it for now and just give it this. So this variable, if we look at it, it's just the WKT string of our projection. So we just tell it that is the coordinate system of the coordinates in here. And then since this data is quite large, so looking at it, it's 3,600 times 1,800 pixels. So it's large enough that data shading actually makes sense. So we say, please set the shape to shade raster, because it's a 2-dimensional data set, so raster makes sense. We want to shade it, so we want to pre-aggregate it. And then we trigger plot map to visualize the data set. So if we do that, we wait a few seconds. So in this case, most of the waiting time was actually the import of data shader. And now we have here our nice map. So we can interactively zoom this map. We can have a look at it until we reach the actual spatial resolution of this map. This is already nice. Again, the widget in this case now already realized that we plotted some data in here. So there are some handy callback functions, like if you click on it, you can get the values of your map and things like that. Yeah. But for now, the next thing that we want to do is we already heard a lot about histograms. So, yes? But yeah. Yeah. Okay, let me know if you manage. Otherwise, so it's supposed to work. So I can try this one again. So basically, we create ourselves a new layer. We plot ourselves the map. You see, it's quite fast.
Do you have the libraries? Because I had this map shader and NCDF also. NC file equals XR open dataset, etc. There I get an error.
Very tough to solve without seeing the error message. Anyone who's capable of dealing with that? Because I guess in the sense of time, it's better to continue. Thank you. So I will just quickly go on a little bit more here. So what we can do is now we have created ourselves this plot, and since we've assigned it to this maps object now knows about the data that it has plotted, so we can use it to add a color bar to the map. And the color bars in EOmaps by default now come with a histogram on top. So directly showing you the distribution of the data that you have in here. Yeah, and again, you can always put yourself a snapshot, a static one, into this map, into the Jupyter notebook. So now we've created the single layer, but usually what we want to do is to create multiple layers, compare them with each other. So we can now just use this map, and instead of exporting it as a static PNG, we can continue and create a new layer on this map with a different data set. So in this case, what we do is we want to visualize the associated quality flag of this data and just put it on top. So we create ourselves a nice color bar. The color bar goes from red to transparent so that we can nicely overlay this color bar on top of the other map. And then we create ourselves a new layer for the quality flag. We assign the data again. We tell it to plot the quality flag parameter. We use the same shape. We provide some additional arguments to the plot function. In this case, we want to have the minimum to be 0, the maximum to be 100, and the color map to be this color map here. And then we can just plot this. So again, it goes pretty fast because the layer is not visible, but we can use the widget to have a look at this layer. So now we can either switch completely to this layer. It looks like this. But we can also switch to this layer and then press Shift and overlay it on top of the other. So it allows you to really quickly create yourself a map. And now we have 2 layers on top of each other. We can interactively compare them, and we nicely see how they work. Again, so here we also have an edit tab actually. So if we want the quality flag layer to have a little bit more transparency, we can have here a slider giving you a transparent overlay of this layer. When it comes to color bars, of course, now we have here one color bar. We can also add the color bar for our quality flag map and put it on a dedicated layer. So in this case now, what we can do is we can look at our map. We can look at our quality flag map. Now it has no color bar because we put the color bar on a dedicated layer. So we can show hide the color bar whenever we want to. So in case we want to overlay it on top of this, we don't want the color bar to be here, so we can put it on a dedicated layer. So this layering, it doesn't matter how many layers you can have hundreds and hundreds of them, so it just allows you to interact with your figure quick and easy. Yeah, and again, you can either programmatically overlay the two layers on top of each other, or you can just do it like this. Yeah, and last but not least, let's pick out a third dataset from here, so we can create ourselves a new layer for the surface state flag. So the surface state flag in this case is a classified dataset. It actually only contains 3 values, 1, 2, and 3. So we plot this. Well, we assign it to our new layer. We use the same shape as before, but in this case we classified the data on the fly into user classified bins, going from 0.5 to 1.5 and then 2.5 and 3.5. And then we use a different color map, and we set the minimum to 0.5 and 3.5. So if we run this again, we create ourselves a third layer. It takes a short moment because in this case it needed to classify the data on the fly, but now we have here a surface state flag layer, and if we look at it, we see it's actually just 3 different values going from 1, 2, 3. So if we want to know what value this is, we can always just click annotate, pick here. So here we have a value of 1, here we have a value of 3, here we have a value of 2. We can create ourselves again a color bar for this one. So since this is a classified data set, it makes sense to get ourselves a classified version of the color bar and put some labels on there. So there's some helper functions to do that. So now we have created ourselves a nice color bar for this classified data. And again, we can go back to our initial layer and have a look at how this layer actually interacts with our quality flag. Or another thing that we can do actually is over here we have the peak layers. So we can always, while looking at one of these layers, we can also just peek on another one. So if we click here, this is going to open up and give you a drop-down list of all the available layers that you've already created. So we can just say we want to peek at the surface state flag, and now we have here a nice widget to interactively look at the surface state flag. So you can change the appearance, you make it a circle, or you can do things like this. So it allows you to quickly assess what's actually going on in your map. Yeah. Another thing is, now that we have created all those data sets, we might want to compare it actually to other things like web map services. So for this, EOmaps provides you with a lot of different web map services. You can add here a new web map layer. So there's practically anything in there that's open access as a web map service to one or the other way. So for example, we can get ourselves the Sentinel-1 global backscatter model, VV polarized layer, and then we can just look at how this looks like. So if we switch to the layer, you realize the first time we clicked on it, it took a while. Yes?
If you accidentally shut that window, big window.
This one?
Yeah, what can you use a plan to reopen it? Or do you want to start it again?
You have to start it again. Like there's no way to, like this is a matplotlib issue in general, like there's no way yet to really revive a matplotlib plot. You have to run the things again. But it should, like we can close it, it should be, the thing is most of the stuff is anyway caged, so we can just recreate ourselves all of these. Yeah, we're already done because so it shouldn't take that long. Yeah. So the thing is, there's loads of web map services that you can add to this. So yeah, we can take ourselves OpenStreetMap. We have several OpenStreetMap layers, and then we can just peek at our OpenStreetMap layer. And now here we have a nice OpenStreetMap overlay. So we can zoom in. So in this case, the web map service actually needs to be reprojected because the map that we've created is in plate carré projection, but the web map service comes in web Mercator. So you can switch your map to Web Mercator, meaning you have to reproject your data. So it's always a drawback. If you want to compare to web map services, is it easier to reproject the web map or the data? With EOmaps, you can do both. So you can just choose. So in this case, loading the web map service is going to be slower, but plotting the data is fast. Yeah, there's loads of layers. If you go to the Edit tab, actually on the web map services, you also have here a question mark button that provides you with different information, especially also on the licensing, because web maps are not free to use. They're free for scientific purposes and for your own good, but not if you implement them in some web maps, in some open access portals. So I tried to collect as much as possible the informations here. And then there's also the code on how to do this programmatically. So you can just copy paste here the code. If you want to permanently add this to your map in a programmatic way, you can just execute this function and the layer will appear. Yeah, so much to that. So the last thing, now we have here our map with a lot of layers. Let's go to one of ours. Maybe this one. And what EOmaps also allows you to do is to assign callbacks to the map. Because when it comes to data analysis, a lot of times what you actually would like to do is click on the map and run a Python function on that pixel and gather all the information that the pixel already provides and then do something with it. So this is done with callbacks in EOmaps. So here we have actually m.cb, which is the accessor for all the callbacks that you can do. And then here we have the options that we can use for assigning actions to our map. So there's click. Click means assign, run something if you click anywhere on the map, completely independent of the data. Then there's key press, which is the same thing, but just pressing buttons on the keyboard. There's move, which is the same thing, just moving your mouse over the map. And then there's pick. And pick means pick the closest data point of the data you've visualized and give me back the ID, the value, and the coordinates of this point, and then run a function. So there are default ones. So in this case, we say, dear soil water index map, please attach a pick callback and create an annotation, and then please execute this callback on all the layers. And the same thing we do for all the others. So please create annotations. For the other two layers, we put them on explicit positions, these annotations. So I will not go into a lot of details with this because we are short in time, but the basic thing is the next time I will click on this so we can get rid of our peak layer. So now we have hard-coded ourselves 3 annotations. In here, the first one is the soil water index one. This gives us the default annotation, this big one here, showing us all the information about the pixel that we have. And then the other 2 are customized ones. So the annotation method also allows you to provide a function for this text. So in this case, we just say, please write SSF equals the value that we picked. And in this case, we just write quality flag equals the value that we picked. And so now we have here on the lower right corner 2 indicators showing us the values of the other 2 layers that are currently hidden. So we can pick ourselves here some point with some quality flag values. So we see that these are the quality flags, but we can also look at this layer and see the value of the quality flag decreases over here. So we can access our hidden layers, we can analyze them. This is just an example. What you can do with it, you can do a lot with it. Just imagine you can run any custom functions that you want in here. So the last thing concerning the basics of data visualization is there's also widgets. So since we're in Jupyter Notebooks, we can use Jupyter widgets, so we can get ourselves Sorry. Here's a button to make it appear always on top again. So we can use ourselves, we can get ourselves a widget inside the Jupyter notebooks that gives us a slider to overlay a dedicated layer, for example, or in this case, we get ourselves some layer buttons that switch to dedicated layers if we click them. So they don't switch to single layers, but they switch to several customized overlays of different layers. So we can do this as we want to, whatever fits to the data analysis that we currently want to do. Yeah, so this is basic data analysis. We used a two-dimensional data set for that, but this is not really necessary. The last thing that I wanted to say about this here is EOmaps also deals with encoded data. So actually the data set that we had in here is encoded. So netcdf or xarray by default decodes the data. So you can turn this off and suddenly you see that all the variables that you have here in our data set, they are supposed to be, where are my variables? Interesting. Because we select one here. So if we would run this in the total, we see that now they're actually unsigned 8-bit integers while they are stored in the file. They're not, they are not, so actually it should be written somewhere in here as well. Here. So we see that this is much smaller in memory, and with EOmaps I can also provide this information, so I can provide the non-decoded dataset in here, and I can just tell it to decode it with respect to the attributes that are defined in here. So here we find ourselves a scale factor and the missing value. So if I run this, it will decode them. So in this case it will load the data and it will decode as we need it. So if I would not decode this, then yeah, this has a much lower memory footprint compared to the others. So it can become really important if you have like tremendously huge data sets. And then last but not least, there's also some quick plotting functions from netcdf. So you can also visualize this as a one-liner just by providing the path to a netcdf. So there are several maps.from file which allow you to plot directly from a netcdf. You just tell it all the information you want, and that's what it's going to do. Yeah. Another thing that sometimes is important is to highlight a certain area on a map. So to create something like this. Also something that people struggle a lot in creating. So in this case, we can just create ourselves a new map, put this netcdf on that we have in here. And now EOmaps provides inset maps. So inset maps, again, follow the same idea. You don't need to learn anything new once you've understood how the basic maps object works. So we just create ourselves a new inset map. The inset map accepts several arguments again, so, but most importantly, it accepts a position and a radius. So the position and the radius will define the location of the map on the globe. But now, actually, this map is in a bad position because it's in the center of the map. Another thing that's usually annoying, so if we go to the widget, here on top we have access to the layout editor, which is something I've created out of the fact that I always wanted to be able to reposition my matplotlib plots interactively, because rearranging matplotlib plots can be a pain in the ass if there are a lot and they have different shapes and sizes. So EOmaps provides you with a layout editor, so you can activate it either by pressing Alt and L, and then you can just reposition whatever axis you have in your map, and then you press Escape to exit it again, and now you have a new layout. And in order to store this layout, there are two possibilities. So you can say m.get me the layout, and then it will print you a dictionary containing all the current positions of the maps that you have in your figure. so like this one. So the next time you can, if you want to recreate it, there is a thing called apply layout. So in this case, we can just copy this in here and then trigger apply layout. So if we recreate this map in here, then add our inset map and then apply this layout, then it's gonna reposition them in the same way as before. So this helps you to quickly adjust the layout of your map. And then if we want to put something on our inset map, so you already see there's a little circle here indicating us the area that we highlight with this map here. So we can just say, please inherit the data from somewhere else, because we already have our data here on this map object. So we just say, please inherit the data from the big one, and then just, this one we don't need, and then just plot it. So if we run this, now it's just gonna plot us here the data from this one, and then actually if we want to get a line between the map and the point, then we can just put a line in here, and we can reposition this as we want to. So it allows you to quickly create yourself a map. So you can put it like this. And then again, you can just copy paste this thing. So you can copy it, and then you can just go to a markdown cell, for example, and paste it in here. So it allows you to work with data and maps quickly.
Sorry, can you also move the inside?
You can zoom in here.
Okay.
Yes. So it's just another map again. So, and since Matplotlib 3.9, we can also zoom while the map is on top of the other map. So that was something we've been working on, but now you can. And the indicator that you see on the map, it actually follows. So now we see that we actually in a square, and then we reach the outer boundary. So yes, you can do that. Okay, so since we're already quite, I don't know when we're supposed to stop because we're quite off the timetable anyways. But so let's quickly jump on into the spatio-temporal analysis. So we're not gonna learn a lot new this time, but I've put a lot of images in here. And so far we just used one of them. So usually what you want to do is to analyze all of them in one go. And so now what we're gonna learn quickly is how EOmaps can help you with that. So again, we import ourselves a lot of stuff. So it's mainly pandas and X-array and EOmaps again. And then we just have a look at all the files that are in this folder. So we have a lot of files in these folders. We want to analyze all of them. So how do we do that? So first, of course, we need to make sure that we understand how one of these files look like, and that they, of course, all need the same kind of structure. So in order to do this, we set up ourselves, so we want to do two things. We want to plot all of the data, and we want to click on the map to show a time slice through the data at the position where we clicked. So that's the task for now. So in order to do that, what we first need to do is write ourselves a function to get the time slice. So in this case, it's a very simple thing. So what we do is we run through all the files, we open them, and based on the ID of the dataset, we extract the value. And then we return a pandas data frame containing this time slice. So how does this function work? So again, I give it the ID and the parameter that I want to extract, and I run it. It runs through all those files and then extracts. So it's slow. It's not the best way to do it, but it does its job. So now we can get ourselves one-dimensional time slices through our image stack. So the next thing that we want to do is create ourselves a callback, so a custom callback function that creates, that visualizes this time series. So this is, again, just very simple. So we create ourselves a function. This function gets the index. So this is the index that we feed in here. It gets the value that we clicked at. It gets a maps object, an axis that we want to plot, the name of the parameter, and the time index that we are just looking at. So a lot of custom arguments, but in EOmaps, callbacks actually get a lot of default ones. So these are the default ones. They are filled up when you click on the map. And the other ones are the ones that you use as your custom ones, so you have to provide them. So what do? We load the data frame, we plot the data frame, we put a marker on the axis, and then in order to remove whatever we plotted the next time, we add them as a temporary artist. So in Matplotlib, everything you plot is an artist. So we plot here our line, and then we add this line as a temporary artist on the pick container. So meaning the next time this event triggers, it's going to remove this artist again. So in order to avoid plotting 100 time series, we plot one. The next time we want to plot, it removes the previous one. So this is our function we want to execute on click. And now the last thing that we need is a function that visualizes our data. So again, this is nothing new. The only thing that's new this time is we don't want to visualize them immediately. We only want to visualize them if we want to see them. So we put everything inside a function. So this function just gets as a first argument a maps object, and then we do whatever we want to do with this maps object. So in this case, it gets a maps object, an axis, a file path, and a parameter. We open our netcdf file, we extract the data we want to see. We assign it, we set the shape, we plot it. Nothing new, we already did that before. And then we assign a few callbacks to this map. And the callback in this case, so here is the important thing. Here we attach a callback, which is the function we defined over here. It says, please, whenever I click on the map and it identifies a data point, please execute this function. And this function here gets our custom parameters that we have. So as a time, we get the timestamp of the netcdf file, the name of the parameter, the axis that we use for plotting. So this we will provide over here. And the other ones, so the index and the value, these are going to be provided by EOmaps when you click on the map. So we can define this function, and now we are ready to actually plot our map. So we create ourselves a map. So let's create the map. Then add an axis to the map. So in this case, we add ourselves a matplotlib axis that we use for the time series visualization. The position is again wrong, but we can just put it somewhere else. So you can use H and V to horizontally and vertically resize them. So we can put it somewhere else such that it looks nice. And then, or we can apply the predefined layout that we had before. And now what we can do is we attach layer activation functions. So the layer activation functions, this is now this function that we defined over here that tells us what we want to do once the layer gets visible. Until the layer is not visible, this is not executed. So we run through all our files and tell it, please, if we look at this layer, do it. So it executed immediately. And if we now look at our widget, we actually see that we have created a lot of layers. All of these are all the data sets in the folder, but they are still lazy, so they have not been plotted. But we can trigger one of them. Now this function is going to trigger. It's going to plot. Once it has read the data, it shows us the data. So we have everything here ready. We can also say, let's peek on another layer like this one. Click on the map. Now it's going to be loaded. It's going to be executed once it's ready. We can combine the two layers with each other. So in this case, whoops, you already see that if I click on the map, so we can add a modifier here so that this is only executed if I press a button. So now we can compare it to a different layer to see what's the difference. But we also attached here our callbacks. So if I click on the map now, the time slice triggers, the time slice plots ourselves here. The time series, so whenever I click, the data point is identified, this function is triggered, it gets the index from here, and with this index we load the data set from our netcdf stack, and then we print the time series over here. So now still all the layers are lazy, but what we can do is, of course, we can also get ourselves a slider in here so that we one moment. Whoops. So that we see where we are, so we can move around here in time with the slider. or what we can do is we can preload all the layers. So in this case now we're going to preload all the layers. So we run through our folder, we preload all the layers so that we can quickly plot them. So you see it's actually quite fast. And now we can here run through our plot. We can really see the indicator, and once we click on the map, we identify our time series, we see where we are actually, and we can go through here and see what's happening. So this is still the global thing, so we can zoom out here and then just see how this thing behaves. And all of this was fully customized, so you can adjust it to whatever data set you want to visualize. So there's very little predefined things over here. Okay, so I don't know how hungry you are. It's already 12:05. I started about 20 minutes late, so I can show you in 5 minutes how the same thing works with irregularly sampled data. Just so in this case, what we have here is a different kind of data set. So before we had a netcdf file containing latitudes, longitudes in a two-dimensionally gridded structure. In this case, so there's a folder with the swath data. So this swath data now is data from the HSUF near real-time surface soil moisture product, and it's provided in a spherical Fibonacci grid. And the format that it is stored is a called contiguous rect array representation. So basically, we have 47,000 values in there, and then we have latitudes and longitudes and time, because each of these observations has its own time. So we can't really, it's not yet a two-dimensional image. So we can load ourselves this data set into a pandas data frame, because it's one-dimensional data structure, so pandas is nice to do. And this is how the data looks like. So if we want to visualize this data, in this case, what I do is I just group them by location ID, so that every location ID has its own unique value. I calculate the mean of this, and this is what I want to visualize. So let's plot the map, and we assign the data. And here this time it's a pandas data frame. So we tell it the two columns of our pandas data frame we want to use as coordinates. We tell it the parameter, and we give it the coordinate reference system we want to use. But this time, since the data is not a raster, we can't visualize it as raster, but we know from, or I know, that the spatial resolution is approximately 6.25 kilometers. So what I'm going to do is I set the shape to geodesic circles with a radius of 6.25 kilometers. And then I'm going to run this. This is going to be a lot slower than raster, but it's not that many data points, so it still works. And now what we have here are a visualization of our data set in terms of ellipses with a radius of 6.25 kilometers. So it allows us to really quickly, and this is not provided in a rectangular data structure, so it allows us to really quickly assess this and plot data sets that are not yet in a format that is super nice and easy to visualize. So using these shapes is nice up to like 500,000 data points. At some point it gets a bit slow, but the good thing is Datashader actually has a shade points, which allows you to shade irregularly sampled data points. So this is also implemented in here. So as the last thing I want to show you is in here, we do the same thing that we did before. We define ourselves an on-layer callback to lazily load all the data sets in our folder. In this case, we use shade points to shade our shapes. And then we just run through all the swath files and plot the data and then show one of the layers. So in this case, we get ourselves here the map. It looks like this. And then we can get ourselves a slider again. And now it's Datashader, so now we can actually, we see they are pretty fast. So the thing that Datashader does is the moment that I zoom in, I actually see that this is a non-rectangular data set. Once I reach a certain level, it switches to a different visualization scheme. But you actually see in some areas that this is a non-rectangular one. So you have yourself your slider, you can go through the image. You can also use other widgets, like in this case, just select them or interactively overlay a lot of them on top of each other. And all of this works with these lines of code. So no matter whether it's a raster data or not, you can really see this. So now we've plotted like, we can see how many layers these are. So if we use this, we will see that we have plotted 24 layers on top of each other, and it still works. We can still compare them with each other. Yeah. Okay, so already past time, so I guess I stop from here. If there are any questions, don't hesitate to contact me. I hope you found it interesting and you're gonna spend some time with EOmaps in the future. So thanks a lot. Good. I don't know about the schedule, if lunch is already done or not. Otherwise, any questions from your side on this? I guess it's quite a lot.
A quick question. When you showed the color ramp with the histogram,
Yes.
is there a way to make this dynamic that you would only show the histogram for the current extent?
In fact, there is. So this is what datashader allows you to do. So datashader allows you to do like a dynamic aggregation. I hope that this works now. So so this thing now, if you provide, you mean like this. So you see, it's not. In this case, I would need to check. So probably what I did here now was not. But in general, yes, there is. So datashader allows you to give you the equal histogram, so it equalizes the histogram on the viewpoint of the data. Yeah. Good. Yes?
This looks great, thank you. I was wondering how active is the maintainer community?
Well, I would love to have more maintainers for that, so it's very hard to find people. I tried to keep it as maintained as possible, so I've undergone the PyOpenSci review recently to get it into a community to ensure that it's to some extent supported. At the moment, it's primarily myself, so I'm active. But of course, being a sole developer is not a good thing, but it's tremendously hard to find people that dedicate time into this. Yeah. Okay, so I was about, okay, that's a good thing, that's a good thing. So if there are more questions, like I ran through the last bits a bit quick, so we can spend the last 10 minutes on questions if there are some more extended ones. So anyone still has a particular interest in what they would like to see or how you can do things?
Can you also plug the figure within the Jupyter notebook?
Yes, that's actually a good point. So initially here we have a list of backends and we did not yet address this, so this is a good thing to do now. So we can open ourselves a new notebook. So so there's different backends. So for now we always used Matplotlib Qt because we wanted to get interactive pop-up figures because they're actually the most responsive. But there's the Matplotlib widget backend, and this widget, it requires you to install the IPy-MPL library, this one here. So if you use this one, where is my file? Here. Then the next time I create a map, this map is gonna appear interactively here in the notebook. And then we can just add ourselves some features. Country borders, why not? And they're gonna appear in here. So you can do the same thing inside a notebook. The problem is, so we could also like, let's add some web map services. So we see a lot of web map services. Let's use this one again, add layer, VV, and put it on a VV layer. So we have now one at a new layer, attach peak layer, and then we peak the VV layer. So we can, so we could do it like this, and then click on this, it's gonna load the web map service, and we have it in here. But now here you see the problem. Matplotlib could use a little bit of help in fixing some tiny issues with the interactive Jupyter backend. So there is a little glitch in the JavaScript end of this code. I'm unfortunately not able to fix it. So it works perfectly for 99% of the cases, but if you have very fast interactions, you can run into little glitches in here. You can always call m.redraw to redraw the map, but also this. So there are some tiny little glitches that are still need to be sorted out. But aside of that, it works perfectly well inside a Jupyter notebook. You can also do other things. So actually the widget backend has problems, but the web HEG has not. So add feature preset ocean, for example. So if we run this and then call m.show, it's going to open us a new web page with our interactive map in it. And this one is super responsive, so this is already nicely done. So you can embed it in an HTML page as well if you want. And there are others. So if you don't want to use the dependency and licensing of Tkinter, you can use of PyQt. You can use the Tkinter. So sometimes you need to restart the kernel to do that. So using Tkinter, you get a very similar thing. But the problem is, at the moment, you lose. So now you see it looks a little bit different. But now we're in the Python native framework. So much less to install, much less licensing problems if you want to distribute it somewhere. But you don't have a widget. That's the problem. That's actually the nice thing about this backend. We can integrate the PyQt event loop in here. If we do this, so it's written in the documentation. If we do this, then we can actually have an interactive plot and an accompanying widget that interacts with the plot that actually lives inside the Jupyter notebook. So that's possible but you need to explicitly integrate the PyQt event loop in here, and then it works just like any others. Yeah, you can draw on the map. You can do different things. Good point. So yeah, there are others depending on whatever you want to use. Yes?
You just showed that you could also do it via a web page or something like that. Is it also possible then to extract the data that it needs so it can run apart from the backend? If you, for instance, just put it on an HTTP server so other people can see it, you draw something, add a lot of layers, and you say like, I want to export this and put it on an HTTP server for anyone to see.
It's never been my use case, so I don't know, to be honest. Like, I mean, extracting the data, basically, at the moment, it knows about all the data. So it means putting all the data on the HTTP server. What you can do is you can run it as a Tornado web service. So you have a Python web server that interacts with the data. That is, in theory, possible. That could do the job. So we tried this a little bit, but my primary aim for this was scientific data analysis so far. So actually to have something for students and for researchers to interact with the data. But yes, it indeed works on a web page.
To export the maps, do you have an easy way to like specify sizes and resolutions and things like that?
Yes.
It's a little easier than
So let's take this map here, for example. So here we have the export section. So we can export it as a 300 dpi PNG with the tight bounding box. And then we can just save it and save it here to the GeoPython folder. So here we should have an image now. So if we open this, now we have exported this as a 300 dpi image. So that works, but Matplotlib is a vector-based library, so actually we can export it as vector graphics. And we can do this not just by saving it, but we could also just copy it. And as we said, the copy-paste functionality interacts with this widget in here. So now I can open Inkscape as a vector data editing software and then just import this map as a vector graphics and then edit it from there. So let's just create ourselves a new document. And now we can just paste it in here. It's probably gonna take a while, but now we have actually a vector graphics here. So if we want to edit this like with minute details, we can now go in here in a vector editing software, and well, it's a lot of different groups, but we can remove or we can change the appearance if I can. Yeah, or we can just remove some countries from our map. Yeah, sorry, I'm not a professional in vector editing softwares, but you get the idea behind this. So if you want to edit this map to really look different in terms of graphical design, you can just create whatever you need as a map with EOmaps and then export it as a vector graphics into a vector editing software and go from there to edit fine-grained details. Aside of that, I mean, you can put little annotations on your map, but that's usually the thing. So if we create this with PyQt, again, so sorry, restarting this kernel. So if we get ourselves an interactive one, where's my map? It's here. So we could, for example, also like there are some ways to add little annotations on your map. Not editable, so like this, and then edit here. But this is usually not like it's nice for some little things, but once you go into the details of putting little labels somewhere, you usually want to go away from an interactive Python map and go into an image editing software. So therefore, exporting it as into whatever format you want. So you can export it as a PDF if you want to, or PNG or whatever. So this is Matplotlib. So whatever Matplotlib supports is supported by this. So this is the real benefit of having a Matplotlib-based plot rather than something that runs natively in the browser. So it's not 100% optimized for the browser, but it gives you a lot of flexibility in what you want to do. So especially for research purposes, it's it can do a lot. But I'd love help from anyone having experience with web development to get the web part to improve on that one. Any other questions? Okay. Yes. Like this? Or so yeah.
Are you clicking to do that?
Yes, sorry. Yes, I'm so used to Matplotlib plots. I'm really sorry. Yes, I click with the right mouse button and then I move the mouse. Yes. So there's like you can zoom into a rectangle. Actually, with the widget, also something that can become handy is you can also here you have a query location. So this query is just the Nomatim OpenStreetMap database, so I can center my map to Italy if I want to, or I can check out Basel. And if I want to see if we are right, we can just add ourselves a web map and see if we really reached Basel, and indeed we did. Again, those features, so here we again see web maps are slow now. So if we say the CRS equals 3857, so which is the native projection of 99% of our web maps, like this. Then the web maps are gonna be blazing fast. So we can create ourselves some default OpenStreetMap layer, switch to this, and now this is gonna be as fast as any other web map that you have. Because now it doesn't need to reproject the web map. Otherwise it needs to, so you can use funky let's see if that works. Funky projections that look nice on a map, but now we need to reproject our web map service on top of that. So if we want to have a land cover map in this projection, we can see how that looks like. Yeah, and now like the web map has been reprojected into this projection, so you can show it. So for me here, the thing really is working with large data sets usually means it's much harder to reproject your data. There's sometimes you reach levels where reprojecting the data is just not really feasible anymore, especially when it's not gridded into a two-dimensional data structure. So then reprojecting everything else is the better idea. And what I've tried to do with EOmaps is to make this nice and easy, so you don't need to handle these things yourself. Also, in general, if you want to deal with GeoPandas, so I think you're going to learn a lot later about that, but there's the add GDF method that just adds a, interesting one. Open too many kernels, I guess. So there's the add geo-data frame directive that just allows you to interact or to add GeoPandas geo-data frames. So anything that I'm doing with vector data, I usually do with GeoPandas. So I just add a geodata frame, and this geodata frame then, you can also use it, you can actually pick data sets. So you can make your geodata frame interactive. So in the documentation, we have some vector data examples. So for example, if you pick one of these and run it, so here we just get ourselves a geodata frame, and then we make it clickable so that we pick out certain features of this geodata frame. So what we do is we just use add geodata frame, and then we assign a picker name. And then what we have is these pick callbacks. Usually they interact with the datasets, but if we use vector data, we just define the name of our picker, and then we tell it, please use this one to attach a certain callback. And now we can run the predefined callbacks, like in this case to highlight a certain area, but we can run any function we want if we click on our map. But yeah, in this case, the library has been developed mostly for data analysis, not so much for vector data, but yeah, there are other libraries that take care of that, and visualizing them with Car2Py and others is, yeah, works. So everything, and maybe one thing that's worth mentioning is it doesn't rip you off anything that Car2Py can do. So if we initialize ourselves a new map, what we get is a matplotlib figure and the Car2Py axis. So the matplotlib figure we can access with m.f, and the matplotlib axis, or in this case the Car2Py geo-axis, we get with m.x. And then here we can just say .plot and access the normal Car2Py method, and now we plotted a line here somewhere on our dataset. And we can use the widget to see where this line actually ended up. So everything the Car2Py does for you, it's still accessible via m.x. The important thing to realize is by default they all end up at the base layer. So if you want to put them on a dedicated layer, you would do it like this. And then you say, split manager, please add an artist. And this artist L should show up on the line layer. So the next time we run this, we see that we have created, in this case we don't even create it. So new layer line. So we create ourselves a new line layer, and then we add this line at this layer. So now it should only show up when we show the line layer. 1 second. Make it a bit bigger and run it. Yeah. And now we have put, this line on the line layer and no longer on the base layer. So if you work with custom artists, you still need to explicitly tell EOmaps at which layer you want to position them. By default, they all end up at the base layer because you need to assign some layer to them. Okay, perfect. Any other questions so far? Otherwise, I think we're all quite hungry. So thank you very much again for your attention, and see you around. Thank you.